Hello everybody, thanks for having me here. It was a bit on short notice because I was one of the speakers originally for the Scala Exchange, which was unfortunately cancelled. I think you've heard all the stories. Today, no Zayo from me, unfortunately. Maybe I'm one of you who was not working with that yet. No magic either, but maybe I can teach you some things about streaming analytics, hopefully. One of my favorite subjects, actually, in the IT world, actually, as what I'm working with right now. So a bit about myself. I'm from the Netherlands. I work there as an independent consultant, primarily in the financial industry. My own background is artificial intelligence. I graduated a long time ago in the pre-machine, the pre-data science world, but it was still like hard coding, neural networks, and genetic algorithms, those kind of things. And you can find me on Twitter or LinkedIn, so happy to connect. So what we're talking about today is streaming analytics, and we call it, or fast data as we call it. And that's an interesting subject that originated from what we call the big data industry. There's plenty of use cases nowadays you can find where data streams are becoming much more interesting to analyze. I've really seen the evolution of like big data in the sense of analyzing huge data sets, which were basically batch oriented. So we had we gather data on a daily basis, for example, on a monthly basis in a bank, for example, and then we run queries on top of that. That was also that was new, like maybe 5 years ago, because then frameworks like Hadoop and Spark arrived, and suddenly we had all the power there to do these kind of queries. The MapReduce algorithm was invented. But I think the last couple of years, much more mature streaming frameworks have come to play that actually also allow these kind of data streams, this kind of massive amounts of data to be analyzed in near real time, so to say. So some examples here on the slide. I work in finance primarily, as I said. So what I've been doing in the last couple of years was, for example, building systems that do fraud detection in real time. So that actually analyze transactions of customers. So when people are paying money, they're spending money online, or they're getting cash from an ATM, or they're paying bills online or whatever on their app, for example. Every transaction has to be validated actually if there is something wrong with that. Maybe there's a fraud case, or there's a hacker, or maybe there's something that's going wrong. And in that split second of like a transaction that is actually being effectuated, you have to make a decision. You have to say, okay, do I block this transaction, or do I allow it, or do I signal a red flag and get back to it? And you might have noticed that sometimes you get for example, when I arrived here in London yesterday, I made a purchase with my debit card. Immediately I got a notification, a text message from my bank saying, hey, we noticed that you're abroad. Is that right? Because if that's not the case, then you should call us, because then somebody might have hacked your account. Other industries, I mean, you see a lot of things there where we analyze the data stream that coming from an online source, in like marketing, when we analyze the click behavior, the click streams of customers, or maybe in healthcare, where we analyze patient data in real time, traffic management, all kinds of interesting topics where these kind of patterns apply. So what I want to do today is to go a little bit back to like the architecture of a software solution that is able to work with these kind of data streams. The examples that I have are with Spark structured streaming, which is technology I think now sort of mature since like a year. It's not my preferred framework there, but it's the most commonly used, because Spark is actually in a lot of organizations already available. And Spark structured streaming is, of course, then the de facto standard to use if you actually are going to build this kind of software. Right. So why Spark structured streaming? Well, is anybody already using streaming or Spark? Yeah, I see quite a few people actually. So then you know this picture already. Yeah? You know what this is. There used to be a core library with what we call the RDD, the Resilient Distributed Data Set. That was the core principle that was in Spark. So that was actually generating distributed data across your cluster, allowing MapReduce kind of algorithms to happen. Very clever in memory, very fast already, but it also had some downside because it was batch oriented. Now they pulled a big trick because they said, hey, what if we make a batch extremely small, like maybe sub-second, so a batch of like 500 milliseconds, something like that. It's still a batch, but it's actually a sequence of batches. You can call it a stream. Well, and they call that Spark Streaming, a library that's already older than 1 year. Yeah, that was a good beginning, but it was more like a trick that they pulled than doing a real-time streaming engine, where you can actually work in real time with every single event that arrives. And that attempt has now been made with Spark Structured Streaming. Interesting thing about that is that it's built on top of Spark SQL, which is actually a querying library that doesn't use the RD anymore. It uses data sets and data frames. So that allows Spark Structured Streaming to have more features, and I will explain a few of them right here. So first thing, when you're building a streaming software, you have to think about the parallelism, of course. One thing that I want to mention here is that you might have a fancy cluster of like 100 nodes of Spark, and all ready to be used, but be careful with how you configure your parallelism. So what Spark actually allows you to do is to configure the parallelism on several levels. And one of them is to configure the parallelism for a job. A job actually is a piece of software that you deploy to your cluster, or you can run it locally if you test it. And every job has a certain priority. And that's not something that Spark immediately takes care of it for you. You have to tell it what the priority is by giving the parallelism levels of this job. So even if you have a job you have a cluster of like 100 nodes, don't use all the 100 nodes for all the jobs that you push to it, because there might be memory overloads, there might be jobs that get in the way of other jobs, and they actually run into memory issues. How do you integrate with Kafka? And maybe I'll skip a step first, because Kafka currently is the de facto data source basically for streams. The open source version at least. I mean, there's also commercial variants of this and also cloud-based versions, but basically they all have the same kind of mechanisms in place as Kafka has. So if you work with, for example, with Amazon, they have Kinesis, which is actually Kafka, but then in cloud. So Kafka, you can see it as the data store for your events. And usually what a Kafka what a Spark job actually is Kafka in, Kafka out. And in between, you read stuff from your Kafka stream, you do your analysis, you put it back on the stream, in a different topic of Kafka. So what you do inside such a job is you consume the events. Usually there's some deserialization going on there. There's some filtering that you want to do there. Maybe because you're not interested in all the events, you might be only in a subset of that. But then the first thing that you do is you window that, because all the events that are on the topic of Kafka in your stream, basically, you can almost say that's an endless ongoing data stream that's there. And that might be interesting. It's like, oh, cool! I can now query on this endless stream of events. But that's not so cool, because then you cannot look infinitely backwards. You cannot. You want to limit your amount of data that you actually are consuming. So in your job, you are usually only interested in a time frame, and that's called a window, a bucket of time. And let's say you're interested in only the last hour of data, or the last week of data. It doesn't really matter, but you have to define what your window of data is, data that you want to respond to. Within that window, once that window is finished, basically, once you actually get a trigger, either from your time or from your event itself, that the window has now been completed, then you want to aggregate that event in that window and basically run the query on top of that window that was gathering in memory while time was passing in your application. That aggregation gives a result. Maybe it's just a count or a sum of events, or maybe it's a highly complicated, machine learning algorithm that gives a forecast or a prediction or does trend analysis and, gives back the results, whatever. But that result of that event will be synced again, and usually you write it back to a new stream. And there's also, of course, syncs that you can write to a database or to a console or wherever you want to put it. So how does it look at Spark? Scala, sorry. Well, the core object here is a Spark session that you have to create to connect to Spark. So this you can see the Spark session as your cluster of Spark that you're actually programming against. You give it some configuration, and you either get or create it. Usually, when you deploy this to a cluster, of course your Spark cluster is already there. But if I run this on my local laptop, the Spark is not running yet in a test or whatever, and it will spin up a new Spark cluster. Some implicits we have to import, and you can always see that this is the SQL context, the SQL context that we have to use. It gives us the ability to really query the streams and the windowed streams that we are actually going to use in our job. And then connecting to Kafka is actually relatively easy. It is a standard implementation that comes together already with Spark libraries, so you don't have to import them in SPT anymore. You just say, okay, I'm going to read a stream from Kafka, and I give it the Kafka parameters, the bootstrap servers, and the topics that I'm interested in. And also the offsets. So the offsets is the type is the time that you want to start reading. And you can start reading, at the latest moment, which is basically at the point that you deploy your job. Or you can say, I want to start maybe when the topic was beginning. So that means that I'm going to replay all the events that have been arriving in Kafka since actually the beginning, when they were available, maybe already a few weeks ago or something. Now, the nice thing about that then, if we have just written this, what is it, 3 lines of code, what you actually will get is a data stream, which is a data frame in SQL, which is just a typical data frame that you can use to map and filter on and do all the functional logic that you are used to when you're programming in but in a normal Spark job, or even in normal Scala applications. So if I would show this to a media or junior engineer in my team, they say, okay, yeah, this is quite easy, right? I have starting with a key value pair. I'm getting the first tuple element, which is the value. And then I'm creating a business object, which is a tweet in this case. And my example is a Twitter stream. I'm filtering it, and then I'm flat mapping it. So I'm pulling it together together to create the words, because I might be interested, for example, in the Twitter trends, in the hashtags, or in the locations, or whatever. But I'm not interested in the tweets itself, but in the individual words that are in the tweet. So I'm mapping that to a tweet, splitting the tweet up in words. And the words, okay, creating a new business class again, which is tweet words. I give it the event time, and we'll come to it later, the time of creation of the tweet itself, because that is interesting for me. That's how I can query in time, basically, and I can pull the time dimension in my Spark queries. And then, well, what is the rest I'm doing? I'm filtering about. I want to ignore some words, probably small words and words with a length that is smaller than some kind of minimum word limit. So you will see this kind of code is not even. You might even not know that this is actually running on a big data cluster of, let's say, 100 Spark nodes that has a lot of complicated logic behind that, where your code is distributed across all these nodes, and actually using the power of this entire Spark cluster. So I mentioned event time a little bit already. This is one of the concepts I want to explain because it's quite an important topic in these kind of streaming algorithms. Maybe not when I'm analyzing tweets, because tweets are what do we care when what time there are. But for other things like the transactions that I just mentioned in the past, it's really important to realize that there's a different timestamp of all these events that come in when they arrive versus when they have been generated. And usually we're interested in the event time, which is the time that the events were actually created. We don't care what time they arrive in our data stream, right? In our application. That's just an arbitrary time that took a while to arrive. There's latency in between that. And even that latency is not a big problem, but these kind of things can be a problem when things get out of order. You see that this one event here arrives actually later in my data stream than the event that followed it. And if you are looking in streaming analytics, where you actually are interested in the order of events to determine a pattern, or determine if a user followed the right patterns in the data or something like that, then you have to look at the event time. The joke that I always make: if you are watching Rise of the Skywalker, in the next week, think about Star Wars. Not the last 3 movies, but the first 3 movies were also out of order. The event time of Star Wars, that's the time where the Star Wars universe was actually happening, a long time ago in history, in a galaxy far, far away, was actually different from the time that we were processing it and watching the movies, because we started with movie 4, right? And then we moved on to movie 1, 2, and 3, etc. All right. So once we have analyzed, once we have gathered all our events from the stream in event time, we're looking at the event time of the windows of the events. Then we have to look at something else, the windows. I always said, we are not so interested in one event in particular. That's usually one event arriving. Yeah, we can do that. We can respond to every single event. But yeah, that's not so interesting. Then you don't need a big data cluster. You can just write regular applications for that, like a software for that. So the power comes to that when you actually will gather all these events in memory and hold them until they are ready to be analyzed. For example, to determine trends, or to determine to compare time windows. This is how you do that is by windowing your events, and a window can be considered as a bucket of time. 3 types of windows there are: sliding, tumbling, and session windows. And the next picture explains, I think, best. Tumbling window is just a window where an event is only part of one window. So the window can be configured to be like 1 hour or maybe even 1 second if you go to real short windows, or whatever you want to give it. And once the window stops, the next window starts. A sliding window is the same, but you give it an interval where this window has to be evaluated at. So even if I have a window of 1 hour, I could say, don't evaluate that window after the whole hour every time, like I do with tumbling window, but evaluate that window of 1 hour every 15 minutes, for example. And because I might be interested in looking backwards for 1 hour, but I want to do that every 15 minutes. So that's interesting. That's technology like Spark allows this for you. You have to realize, of course, that this would lead, if you would use a sliding window, this would lead to much bigger memory loads, because every event that comes in is part of multiple windows. And every window in itself is stored in memory until it's ready to be evaluated, aggregated actually. One last type of window is a session window. You could also look at not the time frame as your reference, but as the event itself. There might be interesting pieces of information in the event itself that trigger the start and end of your window. Unfortunately, that is not in Spark structured streaming yet. So if you want to do something like that, you have to build something like that for yourself. Another favorite framework of mine, Flink, has this already in its library. So if you really need session windows, for example, to look at sessions where the time, whatever, the window that from the moment that the user logged in until he logged out, something like that on a website, you could consider other technologies like Flink to handle it for you. So how does it look in code? Well, it's actually quite, that's the beauty again of Spark. It's the tweet stream that we had previously with all the filtered data, etc. Can be put in a window, and what the developers of Spark actually said, okay, what a window is actually, it's a group. It's a group by function. So this group by is not a group by in the traditional sense of batch processing, or when you would query a database, for example. It's a little bit different, but since the concept is a little bit the same, they just call it also a group by function. And look, what I group by is a window, and the window is this. The window is the event time of the window is the field called created at. This little dollar mark you see here is that we point at a column. So this is one of the implicits that Spark uses for us to make this into the column of the data frame. And I give it a window of 1 hour with a slide of 15 minutes. So this is the example that I just gave, where we have a sliding window of 15 minutes. And then after my window is finished, I will aggregate that window into a function, with a function, sorry. And my function is now a very simple count function. So what I want to do at the end of this window is count all the words that are appeared in that window. Regulars, independent of which kind of tweet they were in. Remember that in the previous example, I split out the tweets in words. You could maybe gather hashtags. If I want now to get the trend of this window, I want to count the words. The count is a standard function in Spark structured streaming. I give it the name count. Of course, I have to store the word itself also with my object that comes out of this aggregation function. And I also store the window end, because this is also a standard column. And this window end gives me the end time of this window. So if I get this out of every string that comes in, I know how many words were in this data stream frame by window. One thing more I want to mention is watermarks, because this combination of windows and event times, of course, makes it really powerful to analyze data streams in what we call near real time, and to really look at the right things for your data stream. But we already mentioned, like the event time is a timestamp which is a little bit later than the time where we actually analyze the events. So what could happen in the terms of lateness is that once an event comes in that signals the end of the window, let's say I say the window is from 1 till 2, and I get an event in my stream that says it's now 1 minute past 2. Then usually I think, okay, that's great, because then I can start analyzing the window, because that is finished. But there might actually be an event that comes in later that had a timestamp of 95 seconds before. So 1 hour 95, which still belonged to the previous window. But then I was already analyzing the window. So I'm too late to incorporate that window. So what I actually want to do is, before I actually start analyzing this window and performing this aggregation function on my window, is to wait a little bit. That little bit of waiting period that I have, that little bit of slack, is signaled by a watermark. So a watermark in itself is another event type, an event that triggers the start of the calculation of the window. And it happens after a while, after I receive the notification that my window actually has completed. And a further remark then, if there is even an event which is later than the watermark, so if there might be some event that comes in even after 2 or 3 seconds, once I actually have started to analyze my window with use of the watermarks, then that event is unfortunately ignored. Again, if you want to do sophisticated things like also including that late event in the previous window, use something like Flink, because that's a much more mature streaming framework that can handle even late events. How does it look like? Well, in Scala, well, you've seen all the code already in my previous slides. The only thing that I added is this line with watermark. As simple as that. So the really complex, that's again the beauty of this code, the really complex mathematics and mechanism behind that actually will wait a while before we actually start analyzing and performing this aggregation function, are all combined in this little statement with watermark, where I look at the event time and I give it a watermark of 1 minute. Okay, I'm almost over time, but one thing I want to say is that if you have more complicated functions like model scoring or model evaluation, what I experienced that is everything that you usually do is very time consuming. So if you would have like an API that you want to call that executes a model for you, you have to give it data, you have to send it over the network, get it back. That API is, I don't know what it will be doing, but it will also be loading a model from somewhere, giving it the features, doing the model evaluation. Takes quite a long time, can take maybe 100 or 200 milliseconds in itself, the whole round trip, which is usually too long if you want to do really real-time stream analysis. So what you could do for that is use a framework and a method called PMML. PMML is actually not a framework, but it's the notation language. The example here is that is a piece of Python code, because PML is just an intermediate format to represent your models in. And the nice thing, it looks like that, it's just XML. And the nice thing about PMML is that you can use another framework called OpenScoring.io to load the models into memory. So what you do actually, you represent them as XML, you load them into memory in your stream, and they're readily available for you to be used in your aggregation functions to run very quickly on top of your event data. Okay, and yeah, that's it. If you want to know more about this kind of mechanisms, streaming, look at Spark Structured Streaming or Flink. You can also read some papers about it. The Google Data Flow papers is recommended. All my code, which does some things more and also connects to database, etc., is online in GitHub, so have a look at it if you would like it. And thanks for your attention. Merry Christmas, and good luck with the Brexit.